4.7 approach with immutable data that is manipulated via structural sharing is that we can keep track of the history of all the versions of the data without exploding the memory of our program. It allows us, for instance, to restore the system back to an earlier state easily. Theo, you told me earlier that it was easy to restore the system to a previous state. Could you show me how? Joe, happily, but before that, I'd like to make sure you understand why keeping track of all the versions of the data is efficient in terms of memory. Theo, I think it's related to the fact that immutable functions use structural sharing, and most of the data between subsequent versions of the state is shared. Tip. Structural sharing allows us to keep many versions of the system state without exploding memory use. Joe, perfect. Now I'll show you how simple it is to undo a mutation. In order to implement an undo mechanism, our system state class needs to have two references to the system data. System data references the current state of the system, and previous system data references the previous state of the system. Theo, that makes sense. Joe, in the commit phase, we update both previous system data and system data. Theo, what does it take to implement an undo mechanism? Joe, the undo is achieved by having system data reference the same version of the system data as previous system data. Theo, could you walk me through an example? Joe, to make things simple, I am going to give a number to each version of the system state. It starts at v0, and each time a mutation is committed, the version is incremented, v1, v2, v3, and so forth. Theo, okay. Joe, let's say that currently our system state is at v12. See figure 4.8. In the system state object, system data refers to v12, and previous system data refers to v11. Theo, so far so good. Joe, now when a mutation is committed, for instance adding a member, both references move forward. System data refers to v13, and previous system data refers to v12. Joe erases the whiteboard to make room for another diagram, figure 4.9. When he's through with his drawing, he shows it to Theo. Theo, I suppose that when we undo the mutation, both references move backward. Joe, in theory, yes, but in practice, it's necessary to maintain a stack of all the state references. For now, to simplify things, we'll maintain only a reference to the previous version. As a consequence, when we undo the mutation, both references refer to v12. Let me draw another diagram on the whiteboard that shows this state. See figure 4.10. Theo, could you show me how to implement this undo mechanism? Joe, actually, it takes only a couple of changes to the system state class. Pay attention to the changes in the commit function. Inside system data before update, we keep a reference to the current state of the system. If the validation and the conflict resolution succeed, we update both previous system data and system data. Theo, I see that implementing system.undo last mutation is simply a matter of having system data refer the same value as previous system data. Joe, as I told you, if we need to allow multiple undos, the code would be a bit more complicated, but you get the idea. Theo, I think so. Although Back to the Future belongs to the realm of science fiction, in DOP, time travel is real. Summary. DOP principle number 3 states that data is immutable. A mutation is an operation that changes the state of the system. In a multi-version approach to state management, mutations are split into calculation and commit phases. All data manipulation must be done via immutable functions. It is forbidden to use the native hash map setter. Structural sharing allows us to create new versions of data efficiently, in terms of memory and computation, where data that is common between the two versions is shared instead of being copied. Structural sharing creates a new version of the data by recursively sharing the parts that don't need to change. A mutation is split in two phases, calculation and commit. A function is said to be immutable when, instead of mutating the data, it creates a new version of the data without changing the data it receives. During the calculation phase, data is manipulated with immutable functions that use structural sharing. The calculation phase is stateless. During the commit phase, we update the system state. The responsibility of the commit phase is to move the system state forward to the version of the state returned by the calculation phase. The data is immutable, but the state reference is mutable. The commit phase is stateful. We validate the system data as a whole. Data validation is decoupled from data manipulation. The fact that the code for the commit phase is common to all the mutations allows us to validate the system state in a central place before we update the state. Keeping the history of the versions of the system data is memory efficient due to structural sharing. Restoring the system to one of its previous states is straightforward due to the clear separation between the calculation phase and the commit phase. In order to use the Lodash immutable functions, we use the Lodash FP module at github.com/lodash/lodash/wiki/fp-guide. Chapter 5. Basic Concurrency Control. Conflicts at Home. This chapter covers managing concurrent mutations with a lock-free optimistic concurrency control strategy, supporting high throughput of reads and writes, reconciliation between concurrent mutations. The changes required for system-managed concurrency are only in the commit phase. They involve a reconciliation algorithm that is universal, in the sense that it can be used in any system where data is represented as an immutable hash map. The implementation of the reconciliation algorithm is efficient because subsequent versions of the system state are created via structural sharing. In the previous chapter, we illustrated the multi-version approach to state management, where a mutation is split into two distinct phases: the calculation phase that deals only with computation, and the commit phase that moves the state reference forward. Usually, in a production system, mutations occur concurrently. Moving the state forward naively, like we did in the previous chapter, is not appropriate. In the present chapter, we are going to learn how to handle concurrent mutations. In DOP, because only the code of the commit phase is stateful, that allows us to use an optimistic concurrency control strategy that doesn't involve any locking mechanism. As a consequence, the throughput of reads and writes is high. The modifications to the code are not trivial, as we have to implement an algorithm that reconciles concurrent mutations. But the modifications impact only the commit phase. The code for the calculation phase stays the same as in the previous chapter. Note: this chapter requires more of an effort to grasp. The flow of the reconciliation algorithm is definitely not trivial, and the implementation involves a non-trivial recursion. Section 5.1. Optimistic Concurrency Control. This morning, before getting to work, Theo takes Joe to the fitness room in the office, and while running on the step machine, the two men talk about their personal lives again. Joe talks about a fight he had last night with Kay, who thinks that he pays more attention to his work than to his family. Theo recounts the painful conflict he had with Jane, his wife, about house budget management. They went to see a therapist, an expert in imago relationship therapy. Imago allowed them to transform their conflict into an opportunity to grow and heal. Joe's ears perk up when he hears the word conflict, because today's lesson is going to be about resolving conflicts and concurrent mutations. A different kind of conflict, though. After a shower and a healthy breakfast, Theo and Joe get down to work. Joe: yesterday I showed you how to manage state with immutable data, assuming that no mutations occur concurrently. Today I'm going to show you how to deal with concurrency control in DOP. Theo: I'm curious to discover what kind of lock mechanisms you use in DOP to synchronize concurrent mutations. Joe: in fact, we don't use any lock mechanism. Theo: why not? Joe: locks hit performance, and if you're not careful, your system could get into a deadlock. Theo, so how do you handle possible conflicts between concurrent mutations in DOP? Joe, in DOP, we use a lock-free strategy called optimistic concurrency control. It's a strategy that allows databases like Elasticsearch to be highly scalable. Note: see elastic.co/Elasticsearch to find out more about Elasticsearch. Theo, you sound like my couples therapist and her anger-free optimistic conflict resolution strategy. Joe, optimistic concurrency control and DOP fit together well. As you will see in a moment, optimistic concurrency control is super efficient when the system data is immutable. Tip: optimistic concurrency control with immutable data is super efficient. Theo, how does it work? Joe, optimistic concurrency control occurs when we let mutations ask forgiveness instead of permission. Tip: optimistic concurrency control occurs when we let mutations ask forgiveness instead of permission. Theo, what do you mean? Joe, the calculation phase does its calculation as if it were the only mutation running. The commit phase is responsible for reconciling concurrent mutations when they don't conflict or for aborting the mutation. Tip: the calculation phase does its calculation as if it were the only mutation running. The commit phase is responsible for trying to reconcile concurrent mutations. Theo, that sounds quite challenging to implement. Joe, dealing with state is never trivial, but the good news is that the code for the reconciliation logic in the commit phase is universal. Theo, does that mean that the same code for the commit phase can be used in any DOP system? Joe, definitely. The code that implements the commit phase assumes nothing about the details of the system, except that the system data is represented as an immutable map. Tip: the implementation of the commit phase in optimistic concurrency control is universal. It can be used in any system where the data is represented by an immutable hash map. Theo, that's awesome. Joe, another cool thing is that handling concurrency doesn't require any changes to the code in the calculation phase. From the calculation phase perspective, the next version of the system data is computed in isolation, as if no other mutations were running concurrently. Joe stands up to illustrate what he means on the whiteboard. While Theo looks at the drawing in Figure 5.1, Joe summarizes the information in Table 5.1. Section 5.2. Reconciliation between concurrent mutations. Theo, could you give me some examples of conflicting concurrent mutations? Joe, sure. One example would be two members trying to borrow the same book copy. Another example might be when two librarians update the publication year of the same book. Theo, you mentioned that the code for the reconciliation logic in the commit phase is universal. What do you mean exactly by reconciliation logic? Joe, it's quite similar to what could happen in Git when you merge a branch back into the main branch. Theo, I love it when the main branch stays the same. Joe, yes, it's nice when the merge has no conflicts and can be done automatically. Do you remember how Git handles the merge in that case? Theo, Git does a fast forward. It updates the main branch to be the same as the merge branch. Joe, right. And what happens when you discover that, meanwhile, another developer has committed their code to the main branch? Theo, then Git does a three-way merge, trying to combine all the changes from the two merge branches with the main branch. Joe, does it always go smoothly? Theo, usually, yes, but it's possible that two developers have modified the same line in the same file. I then have to manually resolve the conflict. I hate when that happens. Tip: in a production system, multiple mutations run concurrently. Before updating the state, we need to reconcile the conflicts between possible concurrent mutations. Joe, in DOP, the reconciliation algorithm in the commit phase is quite similar to a merge in Git, except instead of a manual conflict resolution, we abort the mutation. There are three possibilities to reconcile between possible concurrent mutations: fast forward, three-way merge, or abort. Joe goes to the whiteboard again. He draws the two diagrams shown in figures 5.2 and 5.3. Theo, could you explain in more detail? Joe, when the commit phase of a mutation starts, we have three versions of the system state. Previous, which is the version on which the calculation phase based its computation. Current, which is the current version during the commit phase. And next, which is the version returned by the calculation phase. Theo, why would current be different than previous? Joe, it happens when other mutations have run concurrently with our mutation. Theo, I see. Joe, if we are in a situation where the current state is the same as the previous state, it means that no mutations run concurrently. Therefore, as in Git, we can safely fast forward and update the state of the system with the next version. Theo, what if the state has not stayed the same? Joe, then it means that mutations have run concurrently. We have to check for conflicts in a way similar to the three-way merge used by Git. The difference is that instead of comparing lines, we compare fields of the system hash map. Theo, could you explain that? Joe, we calculate the diff between previous and next, and between previous and current. If the two diffs have no fields in common, then there is no conflict between the mutations that have run concurrently. We can safely apply the changes from previous to next into current. Joe makes his explanation visual with another diagram on the whiteboard. He then shows figure 5.4 to Theo. Theo, what if there is a conflict? Joe, then we abort the mutation. Theo, aborting a user request seems unacceptable. Joe, in fact, in a user-facing system, conflicting concurrent mutations are fairly rare. That's why it's okay to abort and let the user run the mutation again. Here, let me draft a table to show you the differences between Git and DOP. Table 5.2. Theo, great, that helps. But in cases where two mutations update the same field of the same entity, I think it's fair enough to let the user know that the request can't be processed. Tip. In a user-facing system, conflicting concurrent mutations are fairly rare. Section 5.3. Reducing collections. Joe, are you ready to challenge your mind with the implementation of the diff algorithm? Theo, let's take a short coffee break before, if you don't mind. Then I'll be ready to tackle anything. After enjoying a large mug of hot coffee and a few butter cookies, Theo and Joe are back to work. Their discussion of the diff algorithm continues. Joe, in the implementation of the diff algorithm, we're going to reduce collections. Theo, I heard about reducing collections in a talk about FP, but I don't remember the details. Could you remind me how this works? Joe, imagine you want to calculate the sum of the elements in a collection of numbers. With _.reduce, it would look like this. Theo, I don't understand. Joe goes to the whiteboard and writes the description of _.reduce. Theo waits patiently until Joe puts the pen down before looking at the description. Description of _.reduce. _.reduce receives three arguments. COLL, a collection of elements. F, a function that receives two arguments. INITVAL, a value. Logic flow. 1. Initialize current res with INITVAL. 2. For each element X of COLL, update current res with F of current res and X. 3. Return current res. Theo, would you mind if I manually expand the logic flow of that code you just wrote for _.reduce? Joe, I think it's a great idea. Theo, in our case, INITVAL is 0. It means that the first call to F will be F of 0 and 1. Then we'll have this, and finally, this. Joe, I like your manual expansion, Theo. Let's make it visual. Now Theo goes to the whiteboard and draws a diagram. Figure 5.5 shows what that looks like. Theo, it's much clearer now. I think that by implementing my custom version of _.reduce, it will make things 100% clear. It takes Theo much less time than he expected to implement reduce. In no time at all, he shows Joe the code. After checking that Theo's code works as expected, see listing 5.3, Joe is proud of Theo. He seems to be catching on better than he anticipated. Joe, well done. Section 5.4, Structural Difference. Note: this section deals with the implementation of a structural diff algorithm. Feel free to skip this section if you don't want to challenge your mind right now with the details of a sophisticated use of recursion. It won't prevent you from enjoying the rest of the book. You can come back to this section later. Theo, how do you calculate the diff between various versions of the system state? Joe, that's the most challenging part of the reconciliation algorithm. We need to implement a structural diff algorithm for hash maps. Theo, in what sense is the diff structural? Joe, the structural diff algorithm looks at the structure of the hash maps and ignores the order of the fields. Theo, could you give me an example? Joe, let's start with maps without nested fields. Basically, there are three kinds of diffs: field replacement, field addition, and field deletion. In order to make things not too complicated, for now we'll deal only with replacement and addition. Joe once again goes to the whiteboard and draws table 5.3, representing the three kinds of diffs. Theo is thinking the whiteboard is really starting to fill up today. Theo, I noticed that the order of the maps matters a lot. What about nested fields? Joe, it's the same idea, but the nesting makes it a bit more difficult to grasp. Joe changes several of the columns in table 5.3. When he's through, he shows Theo the nested fields in table 5.4. Note: the version of the structural diff algorithm illustrated in this chapter does not deal with deletions. Dealing with deletions is definitely possible, but it requires a more complicated algorithm. Theo, as you said, it's harder to grasp. What about arrays? Joe, we compare the elements of the arrays in order. If they are equal, the diff is null. If they differ, the diff has the value of the second array. Joe summarizes the various kinds of diffs in another table on the whiteboard. Theo looks at the result in table 5.5. Theo, this usage of null is a bit weird, but okay. Is it complicated to implement the structural diff algorithm? Joe, definitely. It took a good dose of mental gymnastics to come up with these 30 lines of code. Joe downloads the code from one of his personal repositories. Theo, with thumb and forefingers touching his chin and his forehead slightly tilted, studies the code. Theo, wow, it involves a recursion inside a reduce. I'm sure Dave will love this, but I'm too tired to understand this code right now. Let's focus on what it does instead of how it does it. In order to familiarize himself with the structural diff algorithm, Theo runs the algorithm with examples from the table that Joe drew on the whiteboard. While Theo occupies his fingers with more and more complicated examples, his mind wanders in the realm of performance. Theo, what about the performance of the structural diff algorithm? It seems that the algorithm goes over the leaves of both pieces of data. Joe, in the general case that's true, but in the case of system data that's manipulated with structural sharing, the code is much more efficient. Theo, what do you mean? Joe, with structural sharing, most of the nested objects are shared between two versions of the system state. Therefore, most of the time, when the code enters diff objects, it will immediately return because data 1 and data 2 are the same. Tip: calculating the diff between two versions of the state is efficient because two hash maps created via structural sharing from the same hash map have most of their nodes in common. Theo, another benefit of immutable data. Let me see how the diff algorithm behaves with concurrent mutations. I think I'll start with a tiny library with no users and a catalog with a single book, Watchman. Joe, I suggest that we start with non-conflicting mutations. What do you suggest? Theo, a mutation that updates the publication year of Watchmen and a mutation that updates both the title of Watchmen and the name of the author of Watchmen. On his laptop, Theo creates 3 versions of the library. He shows Joe his code, where one mutation updates the publication year of Watchmen, and the other one updates the title of Watchmen and the author's name. Theo, I'm curious to see what the diff between previous and current looks like. Joe, run the code and you'll see. Theo runs the code snippets for the structural diff between previous and next, and for the structural diff between previous and current. His curiosity satisfied, Theo finds it's all beginning to make sense. Joe, can you give me the information path of the single field in the structural diff between previous and next? Theo, it's this. Joe, right. And what are the information paths of the fields in the structural diff between previous and current? Theo, it's this for the book title and this for the author's name. Joe, perfect. Now, can you find out how to detect conflicting mutations by inspecting the information paths of the structural diffs? Theo, we need to check if they have an information path in common or not. Joe, exactly. If they have, it means the mutations are conflicting. Theo, but I have no idea how to write code that retrieves the information paths of a nested map. Joe, once again, it's a non-trivial piece of code that involves a recursion inside a reduce. Let me download another piece of code from my repository and show it to you. Theo, let me see if your code works as expected with the structural diffs of the mutations. Theo tests Joe's code with 2 code snippets. The first shows the information paths of the structural diff between previous and next, and the second shows the information paths of the structural diff between previous and current. Theo, nice. I assume that Lodash has a function that checks whether 2 arrays have an element in common? Joe, almost. There is _.intersection, which returns an array of the unique values that are in 2 given arrays. For our purpose, though, we need to check whether the intersection is empty. Here, look at this example. Theo, you told me earlier that in the case of non-conflicting mutations, we can safely patch the changes induced by the transition from previous to next into current. How do you implement that? Joe, we do a recursive merge between current and the diff between previous and next. Theo, does Lodash provide an immutable version of recursive merge? Joe, yes. Here's another example. Take a look at this code. Theo, could it be as simple as this? Joe, indeed. Section 5.5. Implementing the reconciliation algorithm. Joe, all the pieces are now in place to implement our reconciliation algorithm. Theo, what kind of changes are required? Joe, it only requires changes in the code of systemstate.commit. Here, look at this example on my laptop. Theo, how does system consistency do the reconciliation? Joe, the system consistency class starts the reconciliation process by comparing previous and current. If they are the same, then we fast forward and return next. Look at this code for system consistency. Theo, wait a minute. Why do you compare previous and current by reference? You should be comparing them by value, right? And it would be quite expensive to compare all the leaves of the 2 nested hash maps. Joe, that's another benefit of immutable data. When the data is not mutated, it is safe to compare references. If they are the same, we know for sure that the data is the same. Tip. When data is immutable, it is safe to compare by reference, which is super fast. When the references are the same, it means that the data is the same. Theo, what about the implementation of the 3-way merge algorithm? Joe, when previous differs from current, it means that concurrent mutations have run. In order to determine whether there is a conflict, we calculate 2 diffs, the diff between previous and current, and the diff between previous and next. If the intersection between the two diffs is empty, it means there is no conflict. We can safely patch the changes between previous to next into current. Theo takes a closer look at the code for the system consistency class in listing 5.16. He tries to figure out if the code is thread-safe or not. Theo: I think the code for system consistency class is not thread-safe. If there's a context switch between checking whether the system has changed in the system consistency class and the updating of the state in system data class, a mutation might override the changes of a previous mutation. Joe: you are totally right. The code works fine in a single-threaded environment like JavaScript, where concurrency is handled via an event loop. However, in a multi-threaded environment, the code needs to be refined in order to be thread-safe. I'll show you someday. Note: the system consistency class is not thread-safe. We will make it thread-safe in Chapter 8. Theo: I think I understand why you called it optimistic concurrency control. It's because we assume that conflicts don't occur too often, right? Joe: correct. It makes me wonder what your therapist would say about conflicts that cannot be resolved. Are there some cases where it's not possible to reconcile the couple? Theo: I don't think she ever mentioned such a possibility. Joe: she must be a very optimistic person. Summary: optimistic concurrency control allows mutations to ask forgiveness instead of permission. Optimistic concurrency control is lock-free. Managing concurrent mutations of our system state with optimistic concurrency control allows our system to support a high throughput of reads and writes. Optimistic concurrency control with immutable data is super efficient. Before updating the state, we need to reconcile the conflicts between possible concurrent mutations. We reconcile between concurrent mutations in a way that is similar to how Git handles a merge between two branches, either a fast-forward or a three-way merge. The changes required to let our system manage concurrency are only in the commit phase. The calculation phase does its calculation as if it were the only mutation running. The commit phase is responsible for trying to reconcile concurrent mutations. The reconciliation algorithm is universal in the sense that it can be used in any system where the system data is represented as an immutable hash map. The implementation of the reconciliation algorithm is efficient, as it leverages the fact that subsequent versions of the system state are created via structural sharing. In a user-facing system, conflicting concurrent mutations are fairly rare. When we cannot safely reconcile between concurrent mutations, we abort the mutation and ask the user to try again. Calculating the structural diff between two versions of the state is efficient, because two hash maps created via structural sharing from the same hash map have most of their nodes in common. When data is immutable, it is safe to compare by reference, which is fast. When the references are the same, it means that the data is the same. There are three kinds of structural differences between two nested hash maps: replacement, addition, and deletion. Our structural diff algorithm supports replacements and additions, but not deletions. Chapter 6: Unit Tests. Programming at a coffee shop. This chapter covers generation of the minimal data input for a test case,